Good morning, chemistry students. I am obviously recording from my home this morning for you. Happy COVID-19. I hope all of you are well. Know that I wish I had you in the classroom, and I wish we were doing all these cool labs and other fun things. So it is what it is. And I think going through this chapter, so the beginning part was balancing those chemical equations, and the next part are types of chemical reactions. And so I hope kind of as we go through, I'll do some demonstrations for you so that you can witness firsthand some of those types of chemical reactions. We'll do what we can. So you're still learning, and super proud of all of you who are working hard and getting things turned in on time. Some of you need to work a little bit on that. Anyway, so hopefully the balancing equations is going okay. Please shoot any questions to me that you have. I'd be happy to do some demonstrations. Maybe again we can touch base on our Friday. I do like that. I like that if we can get together and ask questions and kind of help each other through things too. All right, so when we talk about chemical equations, there's definitely, some symbols that we see, and I just want to make sure, so this is taken directly from your book, um, and these symbols are obviously really important. So when we look at a chemical equation, we do see the symbol plus, and most of you realize already that separates, either the reactants or the products. So, magnesium plus oxygen yields magnesium oxide. You actually have done that reaction in the lab when you heated magnesium and it turned kind of to that ash looking stuff. That was magnesium oxide. Um, so the arrow we say is the yields. So it yields, it separates reactants from the products. Sometimes with reactants or in reactions, we use a yield arrow that kind of goes in both directions. It may also be written this way. This means that the reaction is taking place both in the forward, but also in the reverse. Reactions that find an equilibrium point are actually occurring in both directions. Um, so sometimes we'll see that. These are really important. And we haven't really looked at this up until now, but in this chapter, these are going to become very, very important. So lowercase s, lowercase l, this is not a one, and lowercase g, these are for solid, liquid, and a gas. And again, when we talk about, especially when we get to, double replacement reactions, which we'll talk about, these are incredibly important. So this just denotes, the state, whether it's a solid, liquid, or gas that's being either combined or produced. And then AQ for aqueous designates that it's a solution in water. So obviously we use a lot of aqueous solutions in chemistry and chemical reactions. A couple of others that you probably haven't really seen before, but we've already used. So there's two ways to indicate that heat is required or used in the reaction. We can either draw this triangle over, oops, over the reaction arrow. Sorry about that. So we either draw this triangle over the reaction arrow, or we can actually write the word heat over the reaction arrow. Okay, so this just means that in this reaction we applied heat. Sometimes it's necessary for the reaction to occur. Sometimes it's just to speed up the reaction. So when we heated magnesium, for example, if we left magnesium long enough, like for months, that reaction with oxygen would occur. It's just oxidation, just like iron would rust. That's oxidation of iron. That would occur naturally, but we don't have time to wait for that, right? So So we definitely speed that up incredibly with heat. Uh, so the other one, again, we don't see this quite as often, but we definitely see it. So sometimes something is necessary in a reaction as perhaps as a catalyst in order for the reaction to occur, but that's not actually used up in the reaction. So we just write, so PT is actually platinum. So sometimes platinum can be used as a catalyst in certain reactions. So that's the example that they give you here. I think a nice biological example of that, if you think of the equation for photosynthesis, um, so if you remember back from biology, and I don't think I can write it on here with this stylus. Um, Back to biology, we have we need several items in order for photosynthesis to occur. We need water, right? So plants have to have water, and they have to have carbon dioxide, and they have to have sunlight. But the sunlight doesn't really get used up. It just sort of provides the energy for that reaction to occur. So sometimes when we write that equation for photosynthesis, sometimes sunlight is written just like this over the reactant arrow because it provides the energy, but it really doesn't participate in any of the chemical reactions, the biochemical reactions that occur there. In photosynthesis, then we know that from that reaction, so the carbon dioxide, water, along with the sunlight, produces glucose, that's sugar, and also oxygen. Thank goodness, because we really appreciate that, right? So that would be kind of a real world example of that. Okay, so the first couple of reactions, pretty simple. We um, combination or synthesis, and you will see this labeled either way. So combination kind of makes sense. Some things are combining. So we usually have two, sometimes three things that are coming together, combining to form one product, or we might have three things coming together to form two products. So this is the kind of the simplest and most typical. We would have a couple of things combining to form one product. So hence the name combination. But synthesis, remember to synthesize means to make. So we also call these synthesis reactions. The exact opposite of that is decomposition reaction. Something's breaking down or decomposing. So a decomposition reaction, we're usually starting with one thing and breaking it down into smaller units. Sometimes we have two things and we're breaking it down into three or four different separate products. But definitely you're starting with something more complex and breaking it down into simpler components. So decomposition. Um, it's, it's what we do with the food molecules that we consume, right, in our bodies. Okay, and so I think the next one, single replacement reaction, where one element replaces a second element in a compound. I think these are pretty exciting reactions, and the way that we know this is a single replacement reaction is there's somebody is single by themselves, and there's a compound, and you'll notice this is an ionic compound. So we are talking about ionic compounds with single replacement reactions. I know this is ionic because one of these is a metal, right? So it's a metal, so copper, nitrate. Remember your ion sheets. So here's the thing. When I give you handouts like your little ion sheet that has a listing of all the ions, remember, I always say if I give you a handout, we need to keep it like forever. It's like something that we're going to use probably for this whole school year. Well, so way back in chapter 7 when I gave you that, well, here we need it again. So single replacement reaction, this is kind of an ionic exchange, if you will. So I always remember it as one analogy that I think of as like, okay, so this couple is going on a date. and they bring their single friend with, but look what happens. At some point, the single friend steals the date, and the other person is bumped out on their single little selves. So it's single replacement reaction. So zinc is a metal. It can only replace the other metal. So zinc is going to replace copper on the copper nitrate. And then copper is by itself singly, and you can see it's a solid here. So this is important too. So the zinc is, zinc is a solid, right? Because it's a metal. The only metal that's not a solid at room temperature is mercury. So zinc is a solid. This is in aqueous solution. So copper nitrate is in aqueous solution dissolved in water. So this has to be in an aqueous solution in order for this to occur. Um, and and there's some other extenuating circumstances that we need to talk about here. So here's the question. Why doesn't this work in the reverse reaction? If I put copper with zinc nitrate, why doesn't the copper bump the zinc off of there? Well, there's a really important piece of information that we need to look at, and I'm going to share that with you. And I've linked it to the HyperDoc, so you have access to something called the activity series chart. So here is why in that reaction that zinc would replace copper, but copper wouldn't replace zinc. Zinc is more reactive than copper, and the more reactive metal is always capable of bumping the other metal of that compound, that ionic compound, but not the other way around. So you have this super cool little chart called the activity series of metals. And I'm going to be honest, down in the bottom part, there's some nonmetals too. So we have both. These are my little scribbles that I've made notation of to clarify. So beginning at the top, these are the most reactive metals, right? And this seems pretty obvious. The metals in this block have things like sodium and potassium, which are pretty explosive in water. There's lots of YouTube videos that will show you that reaction. Please look them up if you don't believe me or if you want to see that. But I think Mr. Hauslog, that's what he usually demonstrated to you in ninth grade physical science. You guys would usually look at that. Anyway, so these are really, really reactive, and it says, so sodium, um, so if you put magnesium, or put sodium into magnesium chloride, because sodium is more reactive, it would bump that magnesium off of that magnesium chloride, and it would become sodium chloride. That's what it's saying. So using this activity series, everything that is, like when I look at aluminum, magnesium is more reactive than aluminum. When I look at zinc, zinc is more reactive than, or less, sorry, manganese is more reactive than zinc, and so on. So as you go further down, these are less and less and less reactive, which kind of makes sense. And then when we get way down here, yeah, copper is not very reactive at all. So these are never going to replace anything above them in reaction. In a reaction, it has to go down this way. So the other thing, all of these in this block will replace hydrogen in water and in acid. So if I put like hydrochloric acid, if I put any of these metals in like HCl, hydrochloric acid, it's going to bump the hydrogen off. The same with these, all will replace hydrogen and acids, but now we lose, yeah, we lose the ability to bump the hydrogen off of the water. And down here, these are mostly non-reactive. Sorry, I don't know how to make my face go away here. That's bad. You don't need to see that right now. So these are pretty non-reactive. These will not replace hydrogen and acids, except in some really rare cases of strong acids. I wanted to add that on here. And then we have a separate little chart here on the bottom where, so fluorine is more reactive than chlorine and so on. So just the same as the metals. So in the case of copper combining with zinc nitrate, we would say there's no reaction. because of that activity series.